lecturing sessions. The third module is all about bandwidth utilization, multiplexing and split spectrum concept. So in the present video session, I'll explain basic categories of multiplexing concept. We'll consider the definition of multiplexing. For example, if you are having two devices like device A and device B. So there is a link between device A and device B in order to communicate each other. Suppose the bandwidth of this link, particular link is greater than the actual required bandwidth in order to do the communications between device A and B. In such instance, the bandwidth can be shared. That means the bandwidth of the medium is greater than the actual bandwidth required of those two devices, then the link can be shared. Multiplexing allows the transmission of multiple signals across a single link. Here, n lines can share the bandwidth of one link. So the diagram shows how we can perform multiplexing and demultiplexing operations. So here we can observe that we are having n input lines, and those n input lines or else multiple streams can be combined into one stream, and that one stream can be traveled through the given link. And across the demultiplexing block, once again, the single stream or one stream can be separated into multiple streams. So we can say that n lines can share the bandwidth of one link. So here we are having one link and n channels. So this block is called as multiplexing block, and this block is called as demultiplexing block. Here the multiplexer block, it will convert n to 1, and demultiplexer block, it will convert 1 to n output lines. So we are having different multiplexing techniques, like the first one is frequency division multiplexing. So in short, we can call it as FDM. The first method is called as frequency division multiplexing. The second method or technique is called as wavelength division multiplexing or WDM. And the third technique is time division multiplexing or else TDM. So FDM and WDM can be used for analog signal, and TDM can be used if the given input signal is digital signal. That means, suppose if you are having analog signal and we have to use TDM technique, means the analog signal need to be converted into digital, and then we can make use of TDM concept. So even in the case of FDM and WDM, suppose we have the input as digital, but we have to make use of either frequency division multiplexing or wavelength division multiplexing. So in such instance, we have to convert digital signal into analog signal. Then only we can use WDM and FDM multiplexing techniques. So the diagram shows the multiplexing techniques, like frequency division multiplexing, wavelength division multiplexing, and time division multiplexing. So FDM and WDM can be used for analog signal, and the time division multiplexing or TDM can be used if the given signal is digital signal. So first we'll take frequency division multiplexing. So the frequency division multiplexing or FDM is an analog technique. So that can be considered whenever the bandwidth of the link is greater than the combined bandwidth of the signals which is to be transmitted. So in such instant, the bandwidth can be shared among the devices. Frequency division multiplexing. In the case of frequency division multiplexing, we can consider n input lines along with multiplexer block and demultiplexer block. In the case of FDM, input signal is modulated as different carrier frequency signals. So those different carrier frequency signals can be combined into one signal, and that respective one signal can be transmitted through the link. So here we can make use of some unused frequency band in order to avoid the interference among the channels. So the channels are separated by strips of unused bandwidth, and that is called as guard band. Unused frequency band can be considered between the channel, and that is called as guard band. So this guard band, it will avoid overlapping as well as interferences between the channels. So now we'll take multiplexing process. In the case of multiplexing concept, initially the source will generate the similar frequency range signal. So now the multiplexer will receive those set of similar frequency range signals, and it will modulate those similar frequency range signals into different carrier frequency signals. So here we can observe that we are having the baseband analog signals as input, and now the modulator, it will modulate the signals with different carrier frequency signals like F1, F2 and F3. So those signals can be combined here in order to generate a single composite signal. So this single composite signal can be sent out over a media link. So demultiplexing process is the reverse operation of multiplexing process. So in the case of multiplexing process, so we have to get back our original input signal or baseband analog signal from the composite signal. So here we can clearly observe that initially the filtering process can be considered. After filtering process, these filters can decompose the multiplexed signal, that is the composite signals, into the respective component signals. So the single component signals can be extracted from the composite signals, and it can be given into the demodulator block. So these individual component signals can be given into the modulator block, and the modulator block separates the carrier signals from the composite signals or component signals. So demodulator will extract the carrier signals from the component signals. So the carrier signal F1 can be extracted over here. So next is carrier signal F2, carrier signal with frequency F2, carrier signal with frequency f3. So finally, the carrier signals can be extracted by the demodulator block from the component signals, and that can be passed through as the output in order to get back our original baseband analog signal. So this is the actual output of the demultiplexer block. The composite signal is converted into the actual original three different signals. Those are nothing but signal 1, signal 2 and signal 3. Five channels, each with 100 kilohertz bandwidth, are to be multiplexed together. What is the minimum bandwidth of the link if there is a need for a guard band of 10 kilohertz between the channel to prevent interference? So first we need to compute the total bandwidth by considering the guard band of around 10 kilohertz. So bandwidth of the link can be computed as sum of bandwidths of different channels, like bandwidth 1 plus bandwidth 2 plus bandwidth 3 plus bandwidth 4 plus bandwidth 5. So we are having the value as 100K plus 100K plus each is of 100 kilohertz. So we get the bandwidth without considering the guard band as 500 kilohertz. So now on consideration of a guard band, and the guard band frequency is given it as 10 kilohertz between the channel. So this is first channel, second, third, fourth and fifth channel. So the guard band between first two channel is 10. This one, once again 10, 10, and the last between fourth and fifth channel is also 10. So 10 into 4, that is equal to 40 kilohertz. So therefore the total bandwidth is equal to 540 kilohertz. 4 data channels, each transmitting at 1 megabits per second, use a satellite channel of 1 megahertz. Design an appropriate configuration using FDM. So we know that the satellite channel will be always analog 1. So here we have to divide the satellite channel into 4 different channels. Each channel will be having the frequency around 250 kilohertz. So here each input signal with the data rate of 1 megabits per second, which is digital 1. So now, since the satellite channel is analog 1, so we have to convert the digital to analog conversion. So here we can make use of QAM concept to convert digital to analog conversion by assuming that 1 megabits per second is modulated so that each 4 bits is modulated to 1 hertz. 4 bits can be modulated in 1 hertz. So for example, if you are having 1 mega divided by 4, so we can get 250 kilohertz. So now after modulation we can have 4 different input signals to FDM as 250 kilohertz analog signal. So that can be combined here using FDM concept to get the output of FDM as 1 megahertz, which can be used by the satellite channel. The analog carrier system. The system which can be used by the telephone company consisting of groups, supergroups, master groups and jumbo group. Initially, in the case of analog hierarchy, 12 voice channels are combined in order to create a single group. And each voice channel has the frequency of 4 kilohertz. So for example, each group consisting of 12 voice channels. Group consisting of 12 voice channels. Individual voice channel has the frequency is around 4 kilohertz. So therefore, the group frequency is 12 into 4, 48 kilohertz. And in order to construct supergroup, we'll be having around 60 voice channels. 60 voice channels means the frequency is equal to 60 into 4 kilohertz. So we'll get the value 240 kilohertz. So similarly, the master group consisting of 600 voice channels, but here we consider the guard band also. So usually while on calculation you get 600 into 4K, you get 2.4 megahertz, but on consideration of guard band, we can consider the frequency in the case of master group will be equal to 2.52 megahertz. So similarly, we can have under jumbo group, we can have around 3600 voice channels and with a frequency of 16.984 megahertz. A very common application of FDM is AM and FM radio broadcasting, where radio uses RS transmission medium and a special band from 530 to 1700, 530 to 1700 hertz is assigned to AM radio. All radio stations need to share this range of frequency. The advanced mobile phone system uses two bands. The first band of 824 to 849 megahertz is used for sending and 869 to 894 megahertz is used for receiving. Each user has a bandwidth of 30 kilohertz in each direction, that is sending and receiving. The 3 kilohertz voice channel is modulated using FM, creating 30 kilohertz of modulated signal. How many people can use their cellular phone simultaneously? So now, first we need to compute each band is of how many megahertz, sending and receiving band frequency range. So each band capacity is equal to, I can compute 849 megahertz minus 824 megahertz. We get the value as 25 megahertz. So now we know the bandwidth of the channel is given as bandwidth is equal to 30 kilohertz. So now we have to compute total number of channels. Total number of channels equal to 250 megahertz divided by 30 kilohertz. So we get the value as 833.33 and we can approximate into even number, that is 832. Therefore, the total number of channels within the system will be around 832 channels. So now, out of these 832 channels, we need to preserve around 42 channels for control purpose. So therefore, remaining channels which can be available for cellular telephone users, that is equal to total number of channels minus number of channels required for controlling purpose. So that is 832 minus 42, that is equal to 790 channels.